Hello everybody, welcome to Unit 5 on rotation. Why don't we get started? So today we're going to be covering rotational motion. And this is a little different concept. We're going to be covering actually a lot of concepts within rotational motion, and almost every concept will have a direct analog to something earlier that we've studied. So let's get started. So we have formulas to model an object's rotation. And the path a particle takes, and given its distance from the axis of rotation, is given by this formula. So we have S, which is kind of like an arc length you could think of, and R, which is the radius, or a radius, and theta, which is the angle that's swept. Now, angular displacement is kind of like, similar to normal displacement that we've discussed, and it's just the difference, in some kind of starting angle position and some kind of final position. This above formula here is a little bit of a misnomer because the theta here represents the angle of a sector, and this is kind of like the arc length. So you could think of something like this over here, where this curved segment is S, this is R over here, and this angle here is theta. A few things. So we're going to be doing a lot of things with angles, and sometimes it gets confusing, like do we use degrees or do we use radians? Well, the rule of thumb is that we're going to use radians for the most part, and if we are using degrees, we're going to have to consciously convert into radians. And the reason why is that radians is a unitless measure versus degrees, which has, of course, the unit of degrees. And yeah, there's 2 pi radians in a circle. Alright, so intuition. So angular speed is how fast does an object rotate, and it's measured in radians per second. So if you imagine like a spinning disk, and if it makes 1 revolution per second, you can think that the angular speed is 1 revolution, which is 2 pi radians per second. So it's just how fast an object rotates. And it's very similar to what we did earlier with velocity. Now, we have a concept of average, and we have a concept of instantaneous angular speed. So, average angular speed is, your starting position minus your final position, except instead of positions, this time it's an angle, divided by the time it takes to travel that far. So, you can start off slow and you can rotate really fast, and if we want the average angular speed, we just take that sector divided by how long it is. Versus instantaneous angular speed, where it's more kind of, in the moment. So when would you use each formula? Well, you would use the second one if you have some kind of let something be rotating such that its position time t is theta equals this over here, where theta is the angle with respect to something. You have some kind of tangible equation, and then you can take the derivative with respect to time, and now you have an instantaneous angular speed. All right. Big point over here. It's positive when we rotate counterclockwise. So you can remember when we did kinematics, we said we would draw an axis, and we would say, all right, this is the positive x-axis, this is the positive y-axis, and sometimes we would be like, it might be easier to actually make positive x in the other direction, right? So we would do something like that. Now, in these problems, when we do rotation, it's very similar, except the convention that we use is that if something is rotating counterclockwise, we say that it's positive. It's rotating in a positive, it has a positive sign. Of course, clockwise is negative. All right, so acceleration. So acceleration, normal acceleration is, how fast an object is speeding up. Angular acceleration is how fast is the rotating speed increasing. So you can think of something revolving, like revolving in a circle, and or revolving around an axis, And if it starts to speed up its rotation, then we say there's an angular acceleration. And angular acceleration has a sign associated with it, which we'll get into in just a second. But we have average angular acceleration is this here, the change in angular speed divided by how long it took to make that change. And instantaneous is very similar, it's just d omega dt. And of course, we'll probably use instantaneous if we have a formula. Now, sign convention. Now, the first one's kind of makes sense to me, at least. It's counterclockwise. It's positive if it's going counterclockwise and speeding up. So this is what we said earlier. If something's moving counterclockwise, it has positive angular velocity. We have positive angular speed in the case of rotating, counterclockwise. So if it's speeding up in that direction, it makes sense to me that it's accelerating. Now, if we go the other way, if we're traveling clockwise, right, and then if we start to slow down, you could think about a force kind of acting in the opposite direction. This thing's trying to go clockwise, but it's just slowing down. It can't anymore because something is opposing its direction, which is the same direction as if it were going counterclockwise and speeding up. So that's how I would imagine it if I ever forget that, this angular acceleration vector, or if I were to think in terms of like a vector kind of mindset, it's going counterclockwise. So either case one, you go, the same direction, you end up speeding up, or if you're going counterclockwise and, this is your acceleration, then you'll end up actually speeding down. So in both of these cases, we say that the angular acceleration is positive. And of course, the other case would be negative. All right, back to units for a second. So, distance is measured now in radians, right? We were doing meters earlier. We were doing translational motion. Now we're doing rotational motion. So we're using radians. Angular speed is measured in radians per second, or just seconds squared. This is a little bit tricky. Sometimes you have, in later classes you might have waves and oscillations where you have hertz, which is just per second, or you have radians per second. So it might get a little confusing. So you have to watch your units. Angular acceleration is radians per second squared, or just seconds per second squared. And yeah, these are vector quantities. We just went over that, right? But in this kind of problem, we're probably going to end up doing, just solving for magnitudes and then assigning it the value at the end. That's kind of just the basic framework of how we do this. Other stuff. So, very different. In kinematics, we were, doing things in different dimensions, right? But in this rotation, there's really only one dimension. There's counterclockwise and clockwise. You're either going to be adding more things rotating counterclockwise, or subtracting things and going clockwise. And very similar, we have our equations of motion. So rigid object angular motion type of equation. So remember our v equals v naught plus at. Well, now we have omega equals omega I plus alpha t. And I'll let you read these equations here. Very similar as last time. Okay. Okay. So we talked about things rotating. Now we're going to say, all right. So you have a rotating disk over here, and now we're going to say, okay, well, this is the center of axis. This is the center of mass. You have something rotating. Now we're going to say, consider a point that's on this disk. So let's say the point is over there. Now we're going to say, what is the velocity of this point, kind of at a moment in time. So this point, of course, it has an angular velocity, but now we're also going to look at this tangential velocity. So the translational velocity vector is always tangent to the circular path. And if I were to draw that out, it would look like that. Okay, so note that while all points on the rotating disk have the same angular speed, they're sweeping out, the same angle in the same amount of time. They do not have the same translational speed. So you can think like, if this were like a merry-go-round, right? If you're at the center, you're barely moving, right? You're just moving to very, very tiny circles. But if you're all the way out, if you're like at this edge, let's say it's like a 1 mile long merry-go-round, you're all the way at the edge. In the same amount of time, you're going to sweep out the same sector as if you were standing right next to the center, but you're going to be traveling so much. You're going to be traveling so fast. So that's really what this translational speed is. So you might have the same rotational speed, but your translational speed is going to be very, very different. In fact, I'm going to say, without even, I'm not looking at this formula over here just yet, but I'll argue that if you're far away from the center, your translational speed is going to be really, really high. So I expect a direct relationship. And yep, if we look at this formula here, we do. We see that our translational speed is equal to our r, which we'll get into in a minute, but it's it's the distance from the center of mass times omega. Now similarly, our tangential acceleration is equal to r times alpha, and our centripetal acceleration, which is v squared over r, if we substitute this first equation in for v squared, we put in r squared omega squared. One of the r's cancels out, so we get r times omega squared. So we can also reformulate our centripetal acceleration formula now. And does this make sense? Kind of does, right? Like if you're at the very end of a merry-go-round, your omega versus very close to the center, your omegas are both the same, but your r's are very different. And if you're further away, you're going to experience more centripetal acceleration. All right, let's go through an example. So we have a small disk 1, of radius 0.1, and it's driven by a motor, and it turns a larger disk 2, of radius 0.5 meters. Disk 2 turns disk 3, which has a radius of 1 meter. The 3 disks are in contact, and there is no slipping. Disk 3 is observed to sweep through 1 complete rotation every 30 seconds. So basically, these are all like, attached. You can think of them kind of like as gears, and they're all moving each other. All right. If disk 1 is rotating clockwise, in which way are the other 2 disks rotating? So if this one here is going clockwise, how is disk 2 moving? Yeah, well, this is kind of a straightforward. So if this is going this way here, disk 2, if you think about it, has like a kind of a gears. Disk 2 would be moving anti-clockwise. So if disk 1 is going clockwise here, disk 2 would be going anti-clockwise. Yeah, I don't have a really good way of drawing that, but I'm sure you can imagine if something's like gears or like this, and one's moving this way here, it's going to move the other one in the opposite direction. Otherwise, you kind of have 2 forces. It wouldn't really make sense. And disk 3, of course, will be moving clockwise. All right, what is the angular speed of disk 3? And the second part is, what is the ratio of the tangential velocities of the rims of each disk to each other? All right, let's start with the first one. So what is the angular speed of disk 3? Well, we're given over here, disk 3 is observed to sweep through 1 complete rotation every 30 seconds. Now, when I think of angular speed, what I'm thinking is that very, earlier slide where angular speed is equal to, the change in angle divided by the change in time. And now I'm thinking that 1 complete rotation how much is one complete rotation in terms of angle? Well, that would be 2 pi radians divided by time, which is 30 seconds. So, oops. Yeah, so I think about that, and you might think, you know, a little bit a different way, exact same thing of thinking about it is like, you know, one rotation divided by 30 seconds times just dimensional analysis here. You know, we know that there's 2 pi radians and one rotation. So we end up getting 2 pi radians divided by 30 seconds, which is the same answer. Alright, part C. What is the ratio of the tangential velocities of the rims of each disk to each other? Well, that's a lot to think about, but I do know some formulas here. So tangential velocity is equal to r times omega. So this is just from our earlier slide. So if we look at, like, you know, v2 equals r2 times omega 2, you know, v3 equals r3 times omega 3. Let's go to the next slide. Oops. If you think about this here, you know, what is the ratio? Well, the omegas are all the same, right? Because we're sweeping, you know, the same angle, or the omegas are not the same. Yeah. So it ends up being like, if you plug into that formula, like it ends up being 1 to 1 to 1. So if you imagine, like, you know, how much a particle is traveling here, it'll end up being the exact same speed as another particle on the rim of another disk. And, you know, one way to reason about this is using these formulas here. And the other way of reasoning about it is, like, if you're at the cusp over here of both rims and you put a particle in each one, there's no, like, reason why one should have a higher tangential speed than to the other one. Alright, so now we're being asked, what is the angular speed of disk 1 and disk 2? Okay, so here we'll go back to, you know, the formulas over here, and we know, you know, v equals r times omega. We know what v is, so v was on this slide over here when we were asked, you know, what is the angular speed, is 0.209. And that's equal to r times omega 1, and then solving for omega 1, we get this. Now, the next part is, if the motor malfunctions, resulting in an angular acceleration of minus 0.1 radians per second for disk 1, what is the disk 2's angular acceleration? Okay, so in this question here, we can basically just put in, you know, a equals alpha times r, you know, from our earlier equation. A is what? So alpha is minus 0.1, and r over here is 0.1 because disk 1, and we know that, you know, the ratio is going to be the same, so we can carry over this a acceleration, the tangential acceleration for disk 1 onto disk 2, and substituting that in, you know, we have a half as much radius, so we get a2 to be double. Okay, so this part's a little trickier. How long would it take disk 3 to stop in accordance with part E? Alright, so here we have alpha 3 is equal to minus 0.01, right? And we have this kinematics equation, remember, like V equals V0 plus AT, right? If we note that, if we want it to stop, that means that the final angular velocity is 0, and the initial one is 0.209, right? And we know our acceleration, we can solve for time, and we get 20.9 seconds. All right, and that's the end of that question. Oops. Okay, so now we're going to look at torque. So torque is a very tricky concept, like to kind of conceptualize, I would say. Force is, push or a pull, makes sense. Torque is the tendency of a force to rotate an object. So what I want you to think about is an object is kind of just sitting there, and a force is, a push or a pull. It's translational motion. You're like moving the entire object. A torque is a specific type of force. So, think of a force, but this force in particular causes the object to rotate. It helps the object rotate. So some of the force, might be doing that. The other force might not be, causing this rotation. So torque itself is a vector, because, force is a vector. And the quantity torque is equal to R cross F. And we'll get into what this is exactly in a second. But just remember that a cross product is, R cross F is the same thing as R times F times the sine of the angle between them. And if we define D to equal R sine phi, then we get F times D also. Now, F is the force applied to the object. R is the distance vector between the rotation axis and the point of application, right? So you're going to apply the force somewhere, right? And it's going to rotate, right, around some axis, and the axis, might be the center of mass. It might be something else. You could have a paper that's, tacked to, with a thumbtack to some board, and it's going to rotate around that axis. So R is that distance from application to the rotation, and phi, of course, is the angle between F and R. And remember, we're taking sine of phi, so if you imagine the unit circle, right, and you have like an angle over here, the sine of this angle here versus the sine of this angle over here. The sine is, the y coordinate, so they'll share the same sine value. So, this is kind of how I think about like angles and sine, and like what to put as the sine, as the SIGN. Anyways, phi is, that angle. D, which we defined on the previous slide over here, we just say that D equal R sine phi, is the moment or lever arm. So if we were to draw this out,
10:33 p.m. Many consider
Alexa, stop. D is this distance from here to here. So you can, you can also like decompose F, right, into a part that's perpendicular to this, R, and a component that's parallel to R here. And there's a lot of different things you can do. So it's helpful, I think, to memorize these two formulations here. Probably just need this formulation. Everything else can be derived from it. Okay, so now, one more thing. So cross product, right? We said it's, A cross B, where A and B are vectors. So right here, they're both vectors. Over here, we take magnitudes. And over here, we take the sine of the angle between. And we use the right-hand rule to tell us, are we going into the page or are we going out of the page? So the right-hand rule, right, you can do it this way here, where, this here points in one direction, this other finger points in the other direction, and your thumb sticks up, like, this would be out of the page here. If you have R here, you have phi here, then you're going into the page. I like to use my whole hand, so I would go like R is going this way, F might be going this way. So first you put your entire, you point your fingers into the direction of R, then you curl in the direction of where F is, and then your thumb sticks up or it sticks down. So you have like R cross phi either this way, or you'd have R cross phi and you would have it going this way. So those are the right hand rules. Just make sure you're using your right hand, like don't use your left hand. All right, so I just want to like very quickly just get a good understanding of torque. So which of the situations will cause the object to rotate quicker? So you can imagine, merry-go-round, imagine some kind of disc here, and they're both identical discs, and you're applying the same force, the magnitude of the force, is the same, except the direction is different. You're applying it at different points. So here you're applying it at kind of like, an angle, and here you're applying directly tangent to the merry-go-round. And I want you to think about which is it harder to rotate, where is it easier to rotate. So I would argue that in this case over here, it's a lot easier. And in the extreme case, this diagram on the left here, you can imagine, if this arrow here was pointing directly at the merry-go-round, it wouldn't rotate at all. And as you slowly start to, move this force more and more, so it's tangent, I feel like it'll be easier because you'll be applying your force in like the perfect direction. You would want to apply a tangent so that way you would cause that rotation. So, it is easier in that case. All right, so, torque is a vector quantity, right? So torque is R cross F, which is a vector and, has a magnitude and a direction. And we say the direction is, into the page or it's out of the page. You might have heard like out of the page being positive and negative being into the page. And, this is like a weird concept, right? Like how can a direction of something be into a page or out of the page? It's really just convention. Like a lot of this is like, you might have like many different torques acting on the same object, but you don't have a good way of aggregating them. Like if I'm applying a force, if you're applying a force, whoever's in the room next to you is applying a force too, and all of our torques are causing the object to rotate in the same direction, right? We don't have a concept of a positive and a minus sign. So what we can say is like, the cross product, like my cross product might be positive, yours might be positive. So we'll just call positive into the page, or we call positive out of the page. And then if we assign a unit to it, if my torque is causing it to move counterclockwise and yours is also, the other person's is also, then we can just sum it up and we can sum up the torques. But if mine's going the opposite direction, causing rotation in the opposite direction, and if we didn't have a sign convention, we wouldn't have a really easy way of aggregating all of this. So I am rambling a little bit, but this is a good thing to think about. Like this out of the page and into the page isn't a very physical thing that you can think about, at least at this point. It's more of like a kind of a bookkeeping easy way to aggregate a bunch of different forces in an easy way. Anyways, the unit of torque is Newton times meter, and this is the same unit of work, but these are very different concepts. And why is it the same unit of work? Well, I'll refer you to the formula of torque again, which is R cross F, and remember force is F times D times sine of theta, or F times D times cosine of phi, depending on how you define the angle. If you think about it, like work is force, which is Newton, times distance, which is meter. Very similar. Now, here's the big moment. So we have, Newton's law, which is F equals ma. We also have torque is equal to, instead of mass, we're going to put I, and instead of acceleration, we put angular acceleration. And I, we call it the moment of inertia. So force equals mass times acceleration. You apply a force, an object has this inherent thing about it called a mass, and your force that you apply causes acceleration. If your mass is really big, your acceleration might be tiny, right? If you try to push an elephant, it'll be very tiny acceleration. Now torque is the exact same thing, except we're not pushing an object anymore, we're causing rotation. So your torque is equal to mass, but the mass instead is not really a mass anymore. It's this kind of, weird mass kind of thing, which is like, do we want to rotate a lot or do we want to rotate a little bit? Like, some things are easier to rotate than others, so to account for that. So that's what this I term is over here. And instead of acceleration, we have angular acceleration, which makes perfect sense, right? We're rotating something, we're going to cause an angular acceleration. So this is how you should think of moment of inertia. It's kind of like mass. In fact, it's very, very similar to mass. It has mass in the formula, but it's more of like the opposition to angular motion instead of translational motion. So I kind of just said what's on this slide, but earlier we did forces and mass, blah blah blah. It's an object's resistance to rotation. And here, let's think about it. So moment of inertia in formula, it'll be discrete. If we have discrete particles, we would have the summation of m times ri squared, where ri, of course, is the same. The distance from the particle to the center of rotation. Or if we have integral form, we would have the integral of r squared times dm. And these two are very similar, right? Because dm is a small, point mass, small particle of mass, and we take this integral to sum up all those particles. Here we can just discretely sum it up. And on the right here we have, a figure skater, and here we say that the moment of inertia is large because, her fingers are at the extreme endpoints here, so the r is very big, versus here, the r is very tiny. So all the mass over here is going to be, like, the only difference between these two pictures, right, is like where her arms are. So when her arms are along her body, the r is very tiny. The m is of course the same. But when her arms are sticking out, this is going to add in a lot of moment of inertia. It's going to add in a lot of resistance. So your I is going to be large. And if we're applying the same torque, tau equals I times alpha, then, if I is large, if t is the same, tau is the same, then our alpha must be small in this first case. So we rotate slowly, we spin slowly. In the second case here, our I is small, so our omega must be large. And we would spin a lot quicker. We would accelerate more, and hence our acceleration is quicker. So, this is more like, this concept here is more related to angular momentum, which we'll cover a little later. But I did want to mention, this analysis on moment of inertia here, and how, if you were to apply a torque, what would happen in both scenarios. And moment of inertia. So this moment of inertia it's a funny thing because it's with respect to a point of rotation. So when we have normal mass, right, we just say, this is a mass of 5, kilograms. We have moment of inertia, it's a little different. It's with respect to a point of rotation because the same object can rotate about many different axes. So we have a different notion of what the moment of inertia is. Let's calculate some. So we'll go by these examples pretty quickly. So calculating moment of inertia. In this example here, we have two masses, and these are particles, so these are discrete. And we can really just, use this first formulation here and sum it up. So let's try that. This here is the, we say moment of inertia with respect to a point. This is our reference point. This is our center of rotation. And, if we just plug it in, we get I equals m times r squared plus 2m times r squared, right? And we get, that didn't print out properly, 3m r squared. Okay, example 2, we're going to calculate the moment of inertia. So earlier we had only two masses. Now we're going to say we have a rod. So in this question here, we don't have a discrete particle system anymore. So we have to use the integral formula. And we know that I equals the integral of, it's r squared dm So earlier, you can just see over here, we have r squared times m, but in the integral formulation, we keep the r squared, but the dm is, is representing now a small piece of mass, which we're going to sum up. We're going to be summing up all the small masses, so the integrals with respect to dm. Anyways, this question is a little tricky because we have a uniform thin rod. So r squared is kind of like, of length L, right? It's passing through the center. So we know that we're going to be doing some sort of integration from minus L over 2 to L over 2. So this whole distance here is L, and we say this here is the origin of 0. This would be positive L over 2. This one here would be minus L over 2. So we're going to be doing some kind of, integration of a bunch of small masses, the usual thing. But it's weird because our integral is not with respect to a position. It's with respect to mass. So we need kind of to develop a relationship between mass and position. So this is a little weird thing, but we're going to do it a few times. So we're going to do it once now. We're going to do it a ton of times next semester in E&M. And it's a good thing to commit to memory this procedure. And what we're going to do is we're going to use density. So I want you to look at this equation for a while and really just replay this part of the video a few times until it makes sense, or just stare at it until it makes sense. dm is a small piece of mass, and I'm going to try to explain it very clearly, as much clear as I can. dr is a differential length. So dr is this tiny, tiny, tiny piece of length. It's like 0.000001 meter. And this dm over here is a small piece of mass. So this dm here is 0.000001 kgs. Now, dm is going to equal to lambda times dr, where lambda is equal to m over L. Okay. So m is the total mass, and L is the length. This makes lambda equal to kilograms per meter. So what you can think about is that a meter, 1 meter of rod is equal to lambda kilograms. This is the density. So lambda is this density. So normally density is, mass divided by volume, right? Density equals mass divided by volume. But when you don't have a 3D object, when you have a 1D object, you do mass divided by the length. That's our density. Now, why is this helpful? it allows us to basically say that m over L is our density. If I want to know, remember, mass is equal to density times dr, which is a small length. And if you think about like units wise, this makes sense, right? dr is like in meters, L is in meters, so you're left with mass. The other way to think about it is like, density is kind of like your how dense something is. So if I give you a little bit, it'll tell me how much mass is in that little bit of snippet here. So if I give it a little piece of length here, the density times that little piece of length is going to tell me how much mass is in that little piece of length here. And that's the relationship that we're going to use. dm equals density times dr, or differential length. Okay, so I hope that wasn't super confusing. Please comment or something if that's confusing, and we'll try to explain it better next year, or we'll post a follow-up. Anyways, now we need to decide the limits of integration from the point of rotation, is where we're integrating from minus L over 2 to L over 2. So I equals this here, right? We put in our limits that we said earlier, minus L over 2 to L over 2. R squared stays the same. dm, now we substitute m over L times dr. Right, we do that over here. Now our integral is just r squared, because the m over L, of course, is something that we can pull out of the integral. And we integrate this, r cubed over 3, substitute in, subtract, we get 1/12 times ml squared. Well, remember this formula, we're going to come back to this, we're going to reuse this later on. Now, there's a cool thing called the parallel axis theorem. And what this is saying is that if you've already done the hard work once, if you've already calculated the center of rotation, if you've already calculated the moment of inertia specifically around the center of mass, then I'll give you a quick formula that'll actually tell me the moment of inertia from another point a distance d away. Parallel axis theorem is saying that the moment of inertia is a moment of inertia of the center of mass plus m, which is the total mass, times d squared. So for example, in this rod scenario, the center of mass, of course, is at the center because it's symmetric. But if I ask you what is the moment of inertia about one of the endpoints, well, you can recalculate this using an integral. This time it would be from minus L to 0. Actually, you could do that, or you could just use this parallel axis theorem and you put in 1/12 ml squared, which is the old one, plus m times the distance that this moved. So it basically moved a distance of L over 2, and you end up getting this over here. And this is kind of the recipe for finding the moment of inertia at some different point. All right, a few more things. So I hope that makes sense. We're going to shift gears for a second and talk about energy. So we talked about forces, talked about energy, right, earlier, same thing now. So we discussed kinetic energy, but objects also have rotational energy. So this is, it takes work to speed up and slow down the rotation of an object. So there's kind of an energy associated with it. And you can think of this as the sum of all the small particles, whizzing around this circle. And we don't want to forget about this term when we apply conservation of energy, because you could have some force, do some work and slow down the rotation, and that would be energy. And just like we have energy, we have power, right? In terms of angular, so power is the rate of work, how much work you're putting in, of torque being delivered. And its relationship is through this equation over here. The derivative of work by time. And it's just torque times the angular velocity. All right. We're going to quickly talk about this. So, we have a ball rolling. It's a very different topic now. We can have pure rotation. So the ball is rotating without slipping. So you can think of a car going down a hill. The tire is rotating and there's no slipping of the tire. You could have pure translation. So you can think of a ball being, or a hockey puck kind of being pushed on ice. There's no, I guess hockey puck's not a good example, but you can think of a ball being pushed on ice. It's translating. The ball itself is not going to rotate. Or you could have both rotation and translation. So a bowling ball, fun fact is, there's a lot of oil on in the bowling lane. So when you bowl a ball, it'll first kind of just skate across the lane. It'll slip, and it'll be purely translational first, and then towards the end it'll start to have traction with the ground, and it'll start to rotate. So there'll be a combination of translation and rotational motion. And the way we can characterize this is pure rotation. There's there's no center of mass, there's no velocity of this, there's no velocity vector that you can put on the center of mass. The center of mass is moving, of course, but it's due to the rotational motion. And here in these other two cases, you would say that there's some kind of velocity of the center of mass, when we were to analyze this here, and that the rotational motion is a result of the center of mass and some other inherent rotation. In the pure translational case, in this middle figure over here, you would have center of mass velocity, but your rotational motion is going to be the same everywhere, and it's going to point in the same direction because the entire ball itself is moving. So in this first case here, you have this bottom vector is going the other way because you're rotating. Now the energy associated, so you would have rotational energy, and you would also have your translational energy. So this is your 1/2 mv squared, and this is going to be 1/2 I omega squared. Now, we also have angular momentum. This is kind of like the skater I was saying earlier. We have linear momentum, we also have angular momentum, and this kind of helps us when the moment of inertia changes. So the skate, she had her arms out and she moved her arms in, and the moment of inertia of that system changed, and as a result we could use angular momentum to help us analyze this. So the instantaneous angular momentum of a particle relative to an axis is this cross product. It's r cross p, where p is the linear momentum, the normal momentum. Now if we expand this out, we get p is equal to m times v, right, which is a vector. So we get m times v times r times sine v. And remember, these are magnitudes in the second formulation, so we can, this commutes. Now torque is then the derivative of the angular momentum with respect to time. Now remember how we said force is kind of the change of momentum? This is very similar. So so angular momentum, we have these two formulations here, and in the special case, if we have a angular momentum of a rotating rigid object, so this just means that the angular momentum of an object spinning, what we would do is we would split up the object into a bunch of masses, and we would say that the total angular momentum is equal to all of the angular momentums of the particles, which is mv mr squared omega, right? Because we can substitute in V equals R times omega, and we would end up getting I times omega. So this is a rotating rigid object. And this is pretty cool, right? Because we have L is equal to I times omega. These are very, like, I is usually a good thing that we can calculate, and omega is probably a given. And there's, two situations here. So you have an isolated system, and you have another isolated system, and then you have some kind of torque acting on the system. And how do we measure that torque? We can say it's a change in the momentum. And the reason why is, angular momentum is conserved. So if it's not conserved, the only thing that could change it is the torque. And the torque is the derivative of it with respect to time. This example is just saying that, like, you have a car that's moving, right? And when you hit the accelerator, if you hit the brakes, it applies a torque on the engine, which changes the angular momentum. All right, here's an example. So we have a long, thin rod of mass m and length L, and it's free to pivot about a fixed pin located at L over 4. The rod is held horizontally by a thin thread attached as shown. The moment of inertia of a rod through its center of mass is 1/12 ml squared. Okay, so we're given the moment of inertia. We actually just computed this earlier, so Now, what is the moment of inertia through the pivot over here at L over 4? Calculate the tension of the thread that supports the rod. All right, so the first part is easy because we can use the parallel axis theorem, right? We know the moment of inertia through the center of mass, and now we're just asking what is it at a certain distance away. Well, how far is it away? The center of mass is at L over 2. This point here is at L over 4. This here is at 0. That means that this distance here is L over 4, which is what we plug in. And we end up getting this. All right, next part. We're going to be asked to calculate the tension. I'm thinking we got to do some kind of balanced forces thing, maybe. Now, so here's the thing. The sum of torque is equal to I times alpha. Now, if there's no angular acceleration, right, because this is at rest, that means the sum of torque is equal to 0. And there's actually two main sources of torque that's acting on this. The first, of course, is this tension over here by this string. The second is actually gravity. So gravity is acting over here at the center of mass, the force of gravity. And the way you can, do these types of questions is that checklist in the Newton's laws. Just go through that checklist, make sure all the forces are taken care of, and from that, see if there's a torque, because a force could apply a torque, and all torque is generated by forces. Okay. The thread is a distance, r away. So this here is actually going to be, this distance from here to here will be 3/4 r. So here to here is the first r. 3/4 L times force of tension, which we'll call T. And the force of gravity is going to be a distance of 1/4 L. And force of gravity is m times g. Now here's a cool thing. So here we can use the right hand rule. So we say r is going, I guess for me it's opposite however I point, but r is going, put your, point in the direction of r, curl your fingers in the direction of the tension, and your thumb should be sticking out of the page, which is positive. So we have a positive sign here. Now for gravity, we would have a negative sign for gravity. So I would point my fingers in the direction of r, curl them for g, and then I'll be pointing into the page, which is negative for gravity. So you have a minus sign. And we can equate the two, and we get the tension is equal to 1/3 of the gravitational force. Part C, determine the angular acceleration of the rod at the moment the thread is cut. So here we can just say that, well, alpha is the angular acceleration is equal to the torque due to gravity, because we've cut out the tension, so there's no force anymore, divided by the moment of inertia. Well, force of gravity, we know that, right, from the previous slide, and we know what I is. And equating the two, we get 12 over 12g divided by 7l. Awesome. Part D. Determine the angular momentum of the rod relative to the pin when the rod reaches a vertical position. Okay, so this is a little trickier. The angular momentum of the rod relative to the pin, so angular momentum is relative to a point, when the rod reaches a vertical position. So the rod will snap over here, we cut it over here, and the rod will become vertical. What is the angular momentum? Well, we can use conservation of energy, right? And we say that the change in potential energy is equal to, initially the center of mass is over here, and then when the rod moves into this position, the center of mass, so this is L over 4, right, will drop L over 4. So the total, this total height over here, displacement, the change in h, is equal to 1/4 L. So you can see here, the initial one is mgh, the second one, we say 0, and the kinetic energy, well, there's no translational kinetic energy, right? Relative to this point, but we do have rotational kinetic energy. And if we put in, 1/2 times I times omega squared, right? Because initially there's nothing, but at the end, we have energy, then we can put that in terms of omega. And we use h is equal to L over 4, and solving for omega, we have the square root over here. So that's what our omega is. Now the angular momentum then is just I times omega, so we take I times omega over here. And I that we've already just solved for. All right, so the last slide here, we're not going to go through the solution, but you can think about it. If the rod reaches the vertical position, it is stuck in an elastic collision at the lower end by a ball of mass m traveling with velocity v. What is the velocity of the ball just after the collision? And we'll post the solution on YouTube. After we get some comments, we'll post the solution, and try this one out. It's an elastic collision, so you can review from last time. What does that mean? Is kinetic energy conserved or is it not conserved? Does elastic mean they stick together or does it not? And then write your before and after equations. Maybe you'll have to use conservation of energy again, and you should get a system of equations that you can solve and get the velocity of the ball right afterwards. And that's it for today. Thank you all for joining, and we'll see you next week.